Hey, I'll go up one notch. Hello, hello. Hello, hello. Yeah. Okay. One item before I get back into material approximately. Problem set 2 is posted. I posted it twice because the first time I posted it, I mangled the 10th problem in the transfer process off from one form into filling in forms on Colab is a pain in the neck, so I transfer it more automatically. And I messed it up. In any case, ignore the first version of that problem set. If you completed it, fine. If you didn't complete it and it automatically submitted your, don't worry about it. Just ignore it. Just do the second corrected version only. Is that okay? Any questions about that? You know, once I've done it, I can't get rid of it. It's okay. Can't fix it. All right. Before going back to talk about seesaws, I thought I'd talk about something else that is rotating. It's never going to get any more relevant than it is right now, and that is the observation, why do hurricanes rotate counterclockwise as you view them from above? Which is to say, they rotate, here in the northern hemisphere, they rotate away from the Earth. Remember the right-hand rule thing? That's their direction. But why are they doing that? You know, this is basically, because you ought to know this, or at least you can use it to impress your friends, why they go. And you know enough to do this. Here's the story. Let's pretend this is the Earth. I think that we have a globe, but who cares? The Earth, as you know, is rotating. It rotates so that the surface heads eastward. So this is the rotation of the Earth as viewed. This is the North Pole up here. So we're here somewhere at this latitude on the rotating Earth. And it's rotating surface east. That means you all are heading east. From the perspective of some visitor coming from another planet looking over at you, they would notice you're heading east and actually quite fast. Here in Charlottesville, you're probably heading east at something like 600 miles an hour relative to just fixed space. Any questions about that idea? If you're closer to the equator, where the Earth is wider, you will be traveling eastward faster, about 1,000 miles an hour. If you're up at the pole, you're just rotating in place. Nothing much is happening. The point of this is that the closer you get to the equator, the faster you are heading east, or things are heading east. All right? So suppose air, for some reason, decides to head towards a certain point on the Earth's surface. And it would do this, we'll see later on in the semester, it does this because of differences in pressure. And if you have low pressure at a certain location on the Earth's surface, air will rush toward it, pushed forward by forces associated with differences in pressure. So the air, let's suppose the air is rushing towards one point. Let's pick a point, I don't know, the B, this point here, whatever that. Air that is closer to the equator and is traveling fast to the east, as it heads toward this point where it becomes closer to the axis of the Earth, it's heading east faster than anything there. So relative to the surface of the Earth and everything there, it drifts eastward. It's going eastward faster than stuff at that location. So it drifts eastward relative to the everything else. You okay with that idea? Everything suppose air that was heading from up north goes that direction. It's traveling eastward relatively slowly. So as it heads toward this point, it's going slower than everything at that point, and it therefore drifts westward relative to everything at that point. So the air from south drifts eastward, air from north drifts westward. It creates a circulation as it goes around. Air that's heading east and west has problems too, but the air basically gets diverted relative to the surface of the Earth. It's obeying inertia. This is an inertia problem. The air is trying to go straight, and it does. And if it encounters places where things are moving faster than it is, it drifts relative to them. They both have inertia. They both do what they were doing. And the air heading towards this point drifts relative to the stuff that's already at that point. And it creates, it looks like it bends from our perspective. From a person watching the Earth go by, they would say the air is heading straight, the other air is heading straight, the surface of the Earth is turning underneath it. Anyway, it ends up deflected, and it creates a circulation that goes around like this. The northward heading air diverts to the east, the southward heading air diverts to the west, and it ends up going in a circle around the point that it was aiming at. And that's the origin of this counterclockwise, as viewed by a space person, circulation of air in the northern hemisphere. Is that good enough, or your questions about that? In the southern hemisphere, hurricanes spin the other way. The whole thing is reversed. Hurricanes don't cross the equator because when they cross the equator, this effect disappears. And the direction of the rotation would have to reverse. Little stuff like the water in a basin or tornadoes, they're too small to notice this inertial effect. So there's mythology around that when you flush a toilet, it turns one way and it swirls one way in the northern hemisphere and swirls the other way in the southern hemisphere. That's just mythology. But for the giant things like hurricanes, where air is rushing toward a center, this deflection effect is dramatic, and it completely dominates the motion and creates this circulating behavior. Northern hemisphere, it's away from the Earth. Southern hemisphere, it's toward the Earth. Right-hand rule. Okay? Questions? All right. The satellite images these days are just filled with these swirling motions caused by inertia. All right, so back to business on seesaws. Get that out of the way. I was talking last time about the fact that riders on a seesaw exert forces on the beam itself, but those forces produce torques, and the mechanism by which they produce torques has to do with a lever arm. So that if I take a beam that's experiencing approximately no torque right now, and it is motionless and staying motionless, meaning it's not being twisted, so its angular velocity is constant. If I push on it at a distance from the pivot, my force and the lever arm from the pivot to where I exert the force can produce a torque. They produce a torque most effectively when they are at right angles to each other, so pushing toward the pivot or away from the pivot doesn't do anything. They're most effective at producing torque when there's a long lever arm, so pushing at the pivot doesn't do anything. So you go away from the pivot, get yourself a lever arm, and push at right angles to the lever arm. That produces a torque. Is that it? You okay with that idea? The direction of the torque follows a right-hand rule. It has to do with which direction the lever arm points and which direction the force points. And the reason for that being interesting is that when you put two kids simultaneously on a seesaw, let me get it balanced to start with, approximately, okay? And we put two kids on it. The kid on the right pushes down at a lever arm toward the right. They produce a torque that, according to the rule, you'll never remember, so don't worry about it, points away from you. That produces a torque away from you. And you can see that's right because the seesaw undergoes some sort of rotation that way. It's an angular acceleration and all that stuff. It's away from you, according to the rule. The kid on the other side of the seesaw also pushes down, but the lever arm is the other way. And so according to the right-hand rule, it points toward you. The torque points toward you. It's in the opposite direction. So the two children sitting on the seesaw exert torques on it that point in opposite directions. Get this right. And the result is those torques cancel. The two torques on this seesaw, one's away from you, a certain strength, one's toward you, a certain strength, the same strength, they sum to zero. No net torque. All right? So that's a balanced seesaw. If you have one really heavy kid instead of two light kids, the heavy kid's going to just cream the other kid, right? So you put the heavy kid in here close. And the point of that is they exert more force on the seesaw beam, but the lever arm's shorter. And the product of short lever arm, big force creates a torque away from you that cancels the torque produced by little force and a big lever arm on the other side. And you get two kids can play seesaw this way, barely, if I can get it, Okay? I really have, we're staring at this slide. I sometimes feel boxed in by my slides. I don't want to spend a semester talking about rotating things, so I want to sort of finish the crucial issues with rotation. This is how you use forces to produce torques. It's part of the story with balancing a seesaw. You try to get the torques to sum to zero. The seesaw is balanced. Everything's simple. I'm going to replace this. Actually, I lost that bearing. Put this back in. I'm just trying to create an expeditious path through the rest of the material. And I'll get rid of that seesaw beam and pop this question up here. If I take Mini-Me, which is a now dated movie icon, there's Mini-Me, okay? I put Mini-Me up here. I actually made Mini-Me for this very purpose up there. It was with football. Mini-Me is pretty well balanced, meaning Mini-Me experiences almost no torque due to gravity. And it got weights on the back, and he's drifted out of balance. He's probably been eating too much. Anyhow, if I want to make Mini-Me undergo angular acceleration clockwise from your view is this way, so it's away from you, according to the official physicist's convention. If I want to make Mini-Me rotate away from you, undergo angular acceleration away from you, which way do I want to smack him? Got 4 choices and a mallet. So do I want to knock the top of his head towards his feet? How many think the top of the head toward the feet? No? Okay, a few. How about the side of his head toward the right? Vast majority. How about the middle of his body toward the right? Okay, how about the side of his feet toward the right? Okay, you're right with B, right? Take that. The idea is this, that when you hit Mini-Me, when I hit Mini-Me, head on the head, is a force at a lever arm from the pivot. So I've got the lever arm I need, and the force is at right angles to the lever arm. That's good. And according to the right-hand rule, which it's in the book, you can figure it out. Your intuition is pretty good at telling you this. The rotation is away from you. It causes angular acceleration away from you. All right? Where this is relevant to all sorts of contact sports or accidental contact sports. If you hit someone on their head straight down, it doesn't cause them to rotate because it's a force directly toward the pivot and therefore along the lever arm, no torque. Same at the middle, no torque. Just mess up my gadget here. If you go at a lever arm and hit somebody at perpendicular to that lever arm, and they have a natural pivot even if there's no, most people don't actually run around with a stake through their stomach. They have a natural pivot, which is their center of mass. If you hit them above their center of mass at an angle somewhat perpendicular to the lever arm from their center of mass to where you hit them, you will cause angular acceleration. And the angular acceleration depends on the direction of the lever arm. If you hit somebody high, they rotate away from you, head away. If you hit them low, they rotate away from you. The feet go away from you. They rotate the other way. So this being the fall, if you go and watch football games, you will see when somebody gets clobbered head high, they begin to rotate head away from the person that clobbered them. If they get hit in the feet, they rotate the other way. The torque reverses. Is that okay? All right. I had one other thing to talk about, and I'm going to go right to it. If you remember, the first question I asked you in opening the story about seesaws was who hits the water first when you have a child that's short and you who's much taller. The two of you lean out over a pool to the same angle, a pool of water. We don't want you to get hurt, okay? So you lean out to the same angle and you let go at the same time. Who hits the water first? Y'all remember this one? Those of you who weren't here before, you're in a shell. A shell? rowing, and you lean out over it, and everybody lets go at once, poop. The shorter people hit the water first. And the reason for that is it's a battle between two things, a torque and the rotational equivalent of mass, namely what I call rotational mass. And I didn't talk about rotational mass explicitly. There is a Newton's second law of rotation that shows it explicitly. Net torques cause angular acceleration, but different objects undergo different angular accelerations depending on their resistance, the measure of their rotational inertia. And that rotational inertia, the measure, it has a formal name which I don't use because it's a mouthful. It's called moment of inertia, which doesn't give you the insight I want it to have. What I call it is rotational mass. This involves a slight oversimplification, but it's good enough. And different objects respond differently to torques because of differences in their rotational mass. Rotational mass isn't some completely new quantity in nature. It's actually constructed out of the ordinary mass and where that ordinary mass is. And so different objects they have a rotational mass that depends on two things. In what part, how much mass they have. The more mass they have, in all likelihood, the more rotational mass they're going to have as well. Rotating a bowling ball is likely to be harder than rotating a golf ball. The other thing that matters is where that mass is located. And the farther that mass is from the pivot, the more it contributes to rotational mass. So this story here, so to go back to this, these objects, they have weight, and therefore the weight being pulled down by the Earth produces a torque on each one about its pivot. And the pivot happens to be their feet, the kids' feet. Your feet, kids' feet, down here where my hands are. That's the pivot. It's forced in, yeah. So they have weight. The weight is, and they have lever arms. The weight of the kid is effectively here, remember center of gravity? And the lever arm is that. So there's a weight down, lever arm here. It's a modest torque that's produced, and that's going to cause angular acceleration. For you, the bigger person, your weight's about twice as much because you have twice as much stuff here. It's located about at the middle of the beam where the center of gravity is. So it's got a bigger pull, being more weight, and it's got a longer lever arm. So there's actually 4 times as much torque on you as there was on the kid. The factor of 2 because you weigh more, and a factor of 2 because you're taller and have a bigger lever arm. So that's 4. Yeah, Dakota?
Would the rotational mass change based on, so if you had the whirlwind and you turned it this way versus like spinning this way, does the rotational mass change?
Like this? Yes. So Dakota's observation or question is the rotational mass different if you do this than if you do this? And the answer is yes. And that's why moment of inertia recognizes that difference. Rotational mass is a little fuzzy about that. This thing, depending on where you put the pivot and which way you rotate it, you get a different rotational mass. And that's one of the details I'm sort of slightly sweeping under the rug. This turns out to be a harder thing to do, to swing this back and forth and experience the rotational mass of the stick like now. Make it rotate one way, make it rotate the other. That involves angular acceleration. And in doing that, you are experiencing its resistance to angular acceleration, which is its rotational mass. This is harder than this. This is particularly easy because all the mass is right near the center, the pivot direction. It's all in here along this line, and you barely even notice it's there. So the details finally, okay, there are lots of details, and I'm trying to just like, okay, we'll leave a lot of them. This stick, it has 4 times the torque on it by virtue of having twice the mass and having that mass twice as far, just to say twice the weight is what matters here. Twice the weight with twice the lever arm, that gives you 2 times 2 is 4. But this stick puts a lot of that mass very far from the pivot, where it contributes like crazy. It actually has 8 times the rotational mass when held like this. These two differ from one another by a factor of 8 in rotational mass. This one's no problem going back and forth. This is hard, as crazy hard. The result is, this is the dominant effect. It's so hard to make this thing undergo angular acceleration that even though it's pulled 4 times as hard, it falls behind the other one. Is that okay? And the demonstration for this is this one. For this, I need two volunteers. 2 people to try this. Please. 1, 2. Good. We're good. These have the same mass and therefore the same weight. And we'll verify this. And your names are? Haley. Haley and Amelia. Haley and Amelia are going to do this. So first I want both of you to hold these just motionless, and you can judge the weights are the same, right? Yeah. Okay. Now each of you take one, hold it right about dead center, as best, and when I say go, try to swing it back and forth, which is a way of measuring its rotational mass, as fast as you can. Ready? Get set? Go. No, not rotate, this way. Okay, as fast as you can. Haley's having trouble relative to Amelia. Can you see that? Trade. Same idea. Hold it pretty much in its middle, at its middle. And now go. Suddenly it's easy for Haley. There's a difference in the rotational mass, and it's a huge difference. Right? You guys can clearly feel this, right? Right. Where do you think the mass is located inside this pipe? This one is easy to rotate back and forth. Where's the mass located? At the center. If you put it at the ends, it contributes like crazy to rotational mass. If you put it at the center, it's not going anywhere, and it contributes very little. So this one's got all the mass hiding inside there. And where do you think the mass is located in Amelia's stick? At the ends. Okay, so this is thank you guys. This is one of these ones where come up after class, try the 2. The difference is striking, particularly if you do it, both of them simultaneously in your own hands. Okay? That's my story for seesaws. I think I've done pretty good justice to it. Yeah, Dakota? What's the relationship between this? This one focuses this formula focuses entirely on the world of rotation and sets aside forces. What are those? We don't even know what they are. This one recognizes that if you exert a torque on something, and it's the only torque acting on it, or equivalently you exert a net torque on something, so that you basically want to get rid of it's just one torque we're dealing with. If you exert a torque on it, it's going to undergo angular acceleration. And how much angular acceleration? So basically it says torques cause angular accelerations. In the same way that Newton's second law, the ordinary one, says that forces cause accelerations. So torques cause angular accelerations. They don't cause angular velocity. They cause the acceleration, the change in angular velocity. And there's a resistance you have to go battle against. And the resistance is this rotational mass. So if you twist an object with a certain torque, it'll undergo a certain angular acceleration. If you double the rotational mass of that object, it'll undergo half the angular acceleration. Okay? Yeah, Kate. What's the difference between a torque and a force? A torque is the influence that causes angular acceleration. A force is the influence that causes ordinary acceleration. So they're different in their effect on things. If you twist a basketball, if I exert a torque on it, it's going to start rotating. It's going to rotate differently. I'm going to change its angular velocity. If I exert a force on it, it's going to accelerate. It's going to go somewhere. You can do both at once, and often do, but they have different effects on the behavior stuff. And the other thing is you can produce a torque with a force, and you can produce a force with a torque. So I can launch kid 1. I'm going to push a force. I'm going to exert a force here, which is going to cause the beam to undergo angular acceleration, which is going to cause this side to rise and produce a force, exert a force on it's going force to rotation, the world of rotation by way of a torque, to force, right? Okay? He survived. So you can go back, they go back and forth. They're not independent things. They have nothing to do with each other. Sometimes you cause both. If I push the bottom of this ball to your right, it's going to it's the only force acting on the ball, so the ball's going to accelerate to the right. It is, however, at a lever arm relative to the center of mass of the ball, its natural pivot. I'm going to also simultaneously produce a torque on the ball about its center of mass. And it accelerates and it begins rotating. It does both. So it often happens. I'm thinking you watch people shooting free throws. They're doing all this stuff. You push in the right place, you get the right rotation you want and the acceleration you want. All right. I won't even try to shoot a free throw. All right. Yeah, okay, I'm going to stop with seesaws. I think I've done my job. So on to wheels. In part, I'm trying to cover the territory that I want to cover in order to talk about, in order to prepare you for the problem set which is due on Wednesday. So the world of wheels. Wheels is a venue in which to talk about friction. So up until now, I've been trying to just ignore friction or just make it unimportant. Air resistance will remain unimportant for a while. We'll get to it eventually, but not yet. So now it's time to bring friction into the story. And start off with this question. You've got a souped up car, lots and lots of power under the hood. And yeah, I guess I would say, I'm thinking now Tesla now. When I wrote the question, there weren't electric cars around that were worth anything. I mean, okay, Prius, but anyhow, you get the idea. So, you're at a light, the light turns green, and you decide to cross the intersection as fast as possible. You want to pick up speed as quickly as possible. Therefore, you want the biggest possible forward force. Do you or do you not want to skid the wheels, spin them, so you burn rubber? How many think that you'll get the fastest acceleration if you do skid the wheels? How many think you'll get the fastest acceleration if you do not? You just barely don't skid the wheels. Yeah, it turns out that the not skidding is more effective in almost all cases than skidding them. It summons, both of them will summon a forward frictional force from the ground. That is, the ground will push the car forward as these wheels try to turn. The force that pushes you forward when you skid the wheels is technically a different, it's named differently, and it tends to be weaker than the frictional force that pushes you forward when the wheels do not skid. So it's not always true, and there are reasons why, like for example, drag racers will actually deliberately spin their wheels to get them hot and sticky. They're gluing their wheel to the pavement to get a tremendous forward force. That's a whole nother story. Okay, so friction, where's friction? What's the role of friction? Friction makes things without wheels have trouble moving across surfaces. They skid to a stop. And this is part of the reason why it's sort of human nature to think that when you push on something, it moves, and when you stop pushing on it, it stops. It's because friction is so hard to get away from. So if you have a wagon, as I do, this is still the same wagon that I've never installed wheels on, and I keep meaning to trade the two just to give this one a time in the sun, but I haven't done it yet. Okay, so this wagon, if you push on it, it moves. If you don't push on it, it stops. That's not because nature says that forces cause velocity. It's because there's a second force that's showing up despite my wanting it not to be there, and that's a force of friction. And it's slowing that thing to a stop, and we'll come to it in a second. Friction wastes energy, or can waste energy and cause wear. Friction does not always waste energy, but it often does. It certainly does in the case of me skidding this thing across. And I need to tell you what it means to waste energy and why it's wasted. Wheels can mitigate this effect. If you put wheels on the wagon, as the lucky wagon here experiences, this, even though it's often experiencing a type of friction, it doesn't waste energy. And it's able to basically to show you inertia again. If I push on it, in contrast to this guy, which slows to a stop when I stop pushing, this guy accelerates when I push and then coasts when I stop pushing. So it's showing you that forces actually cause acceleration. Push on it, it accelerates. All right, and wheels can also propel vehicles. So not all wheels just roll to keep things from skidding to a stop. Some wheels are used to push the vehicle forward. Really what they're doing is they're getting the ground, with the help of the ground, they're getting the ground to push the vehicle forward. All right, my set of 6 questions to go after, the how and why questions. And the first one then is, why does a wagon need wheels? And this is, not surprisingly, just an introduction to friction. And friction, so no wheels today. Sorry, bucko, you get the wheelless wagon. This wagon skids to a stop whenever I get it going. And it skids to a stop whether I push it to the right and get it going to the right, or push it to the left and get it going to the left. Friction is clever. It figures out which way to push. And what it's really doing, first of all, friction generically is the name for the forces that act on 2 surfaces that are moving across one another. So they're in relative motion. So whether one's stationary and the other one's moving, or whether the other one's stationary and the bottom one's moving, or whether they're both moving, what friction is doing between the 2 of them is it's pushing on them such that they will tend to go to the same velocity. So in this case, whatever my hands are doing, each hand is trying to make the other hand move with it at its velocity. They will often compromise. Sometimes the compromise is lopsided. For example, when this guy is skidding to the right, the wagon wants the table to head to the right. The table wants the wagon to stop moving to the right. And the negotiation between the 2 is completely lopsided. The table completely wins. The wagon ends up moving at the table's velocity. And this has to do with mass stuff. The table's obviously got more mass. And it's attached to the whole Earth. So it's the winner in that. But my point is that the 2 are fighting over relative velocity. And they want to go to the same velocity, and they will do that given some time. Okay? Friction differs from support forces. How? Support forces, if you remember, are exerted by 2 objects on one another perpendicular to the surfaces of the objects. So right now, the table is exerting a support force on the wagon straight up, because the table is horizontal, and perpendicular to horizontal is straight up. The wagon is exerting a support force, the name doesn't sound right, but it's a support force down on the table. It doesn't want the table coming up through it. So it pushes down on the table, perpendicular to its surface. Those 2 forces happen to be equal and opposite because they are a Newton's third law pair. The table exerts a support force on the wagon exerts a support force on the table. That's a pair, and they have to be equal and opposite. Where's friction? Friction, instead of being perpendicular to surfaces, is along surfaces, parallel to them. So when this guy's skidding along, the table is exerting a force on the wagon parallel to the table surface. That's friction. And at the same time, the wagon is exerting a frictional force on the table perpendicular to the wagon surface, which is also horizontal. So they're pushing on each other. And this is what gummed me up when I first started talking about friction forces. What was going through my head is they always show up as Newton's third law pairs. If my hand is skidding to the right on the table, it's exerting a rightward frictional force on the table. At the same time, the table is exerting a leftward frictional force on my hand. They go together. Newton's third law pair, equal and opposite. You okay with that? As always, they don't cancel because you never add them up. Why? Because they act on different objects. So the table's frictional force on the wagon, it's a frictional force to the left. The table is pushing the wagon to the left, which causes it to accelerate toward the left. It's the only force horizontally on the wagon. And it slows it to a stop, right? That's why the wagon slowed to stop. The table pushed it to the left and sucked its forward motion out. At the same time, the wagon pushed the table with a frictional force to the right and the table accelerated to the right, but just not very much. You could barely notice it. No, you couldn't notice it. It's just too dinky. Okay? As an aside that I've sort of done before is when I do this, right, I push on the ground with, in this case, a support force, but I could have used a frictional force if I wanted to. I'd have to skid against the walls. Okay? I pushed the earth down, the earth pushed me up. I accelerated up briefly. The earth accelerated down briefly, too, but not very much. So if somebody ever asks you, I'm sure I asked my father as a kid, like, if I jump up, does the earth, and I push the earth down, does the earth actually go somewhere? Yes, son, which is not how we would talk. But okay, the answer is yes. So when this ever occurs to you, or occurs, you do indeed push the entire earth down, and it does accelerate down. Just so little, because it's so massive, you would never notice it. And if you exert a torque on it, wow, like that, okay? I get to have fun. All right. When you do that, the entire earth undergoes angular acceleration, just not very much, okay? Yes, during my childhood, there was concern that the Chinese, who at that time were red Chinese, would somehow destroy the United States by all getting on ladders and jumping off simultaneously and pushing the whole earth. In some sense, paranoia, it shows up in every generation. I didn't say that. Okay. Why is sliding a box across the floor usually hardest at the start? And let me show you that this is the case. It's not always the case. It's a general rule. This is true. So I've got a spring scale that will tell you how hard I'm pushing on, or pulling in this case, on the wheelless wagon. And for a little extra degree of difficulty, we're going to put you in the wagon. Okay? So you're in a wagon with no wheels on the sidewalk, and if you've ever pulled, you haven't, pulled somebody in a wagon with no wheels, it's not easy, right? Because they're stuck in place. And as I pull a little to the left, nothing happens. I pull a little more to the left, nothing happens. What's going on here? There's no sliding going on, and yet the wagon is sort of stuck in place. Well, what the wagon is experiencing right now is still a frictional force. It's called a static frictional force. Static being, no movement. It's a force that comes because the two surfaces are acting to move at the same velocity. It happens to be same relative velocity, and the relative velocity is at present 0. They are moving at the same velocity right now. It happens to be 0 for both of them, but we could have the whole thing moving to your left and it would still work. These two surfaces are resisting relative motion, and which has not yet started, and that's static friction. Technically, why are there forces like that? Why do these things not like to start sliding? Microscopically, the two surfaces are not perfectly smooth. They fundamentally have to have some structure in them, if nothing else, atomic structure. But they have some structure, and if you think of a structured surface from the bottom of the wagon pointing down and a structured surface from the table pointing up, it's kind of like two hairbrushes with their bristles a little bit interlocked, and you get them interlocked. It's hard to slide them across each other. So they're fighting each other with support forces associated with the structure. Okay? So initially, it's hard to get them started. And in order to get them, right now, I'm pulling with 4 newtons to the left. The table is exerting a 4 Newton frictional force, specifically a static frictional force, on the bottom of the wagon, and basically canceling the overall force. I can't get it started. 8, 10, static friction is clever. It can figure out just how hard to push on the bottom surface to stop on the wagon, the bottom surface of the wagon, to prevent the wagon from beginning to slide across the table. There's a limit to static friction, however, just as there's a limit to how well the bristles of a brush can hold the two brushes in place. If you push hard enough, if nothing, you'll get them to go. I mean, at worst came to worst, you'd actually tear the bristles right off one or both of the brushes. Eventually you can win, get them moving. Same here. If I pull hard enough, the wagon will begin to slide. How hard? There it went. I got all the way to 20 before it started to slide, and now I can keep it sliding with only 10. Did you notice that effect? That before it began to slide, I was able to pull harder and harder, 10, 20, 10, 15. When I hit 20, I got the movement started. So it stopped being static friction, and it started being another kind of friction, a friction in which the bristles, in effect, are now bouncing along each other. And I call that sliding friction, just to give it an identifiable name. It's also called dynamic friction, but sliding friction. And it was not as strong as static friction. The starting process was harder than the continuing process. It takes a little while for the bristles to settle in, so I might not get to 20 anymore. Let's give it a shot. 12, 14. Once I got to 14, it skidded, it started moving, and now I'm at 10 again. So the point of this is, static friction is adjustable. The force it exerts is adjustable. It does everything it needs to do to keep motion from starting. And it can get quite strong. Once the motion begins, once the two surfaces begin moving across each other, the force is now sliding friction. It's somewhat different in character. Among other things, it's not adjustable anymore. It has only to do with the two surfaces themselves sliding. It's a specific amount. And it's typically weaker than the force of static friction. Not always, but mostly. And this is why that first question I asked you about skidding your car wheels to propel yourself forward, do you want to skid or not skid? You don't want to skid. So here's your car sitting there on its wheels, and when the wheels are rolling smoothly, they're not skidding, the bottom of the wheel, so this is sort of getting ahead of ourselves, but it's okay. The bottom of the wheel doesn't skid, it lands and leaves. It comes down, rolls, and then comes up, but it never actually moves across the surface. And the result of that is the frictional forces between rolling wheels on the ground are static frictional forces, the forces of two surfaces that are not skidding across each other yet. They're considering it maybe, but they're not doing it yet. So if you roll the wheels, you get static friction. If you skid the wheels, it's sliding friction. Can you follow that idea, or questions about that one? And as I've showed you already, sliding friction is typically weaker than static friction. So if you can let the wheels just do, I think of touch and release. You can play wheel in your own hand, right? These were apps when I was a kid. Yeah. When a wheel is rolling, it's experiencing, in principle, only static friction between its surface and the surface that is rolling on. Is that okay? Because it never actually moves relative to the surface. There are, I should say, these two names of friction, sliding friction, static friction, they're not the whole toolbox of frictions. There are other kinds of friction around, and we'll see that frictions typically, some of the frictions waste energy. And there is a third friction among many that may actually be called rolling friction. When a tire is not properly inflated, think about what happens when a tire lands and leaves, when it's soft. When it lands, instead of just landing hard surface on hard surface, it's squishy surface on hard surface. And that surface changes shape as it's mushing into the pavement and then unmushing from the pavement. And that changing of shape can waste energy. And so there's a friction associated with underinflated tires. This is why you're told correctly to keep the tires of your car or your bicycle properly inflated. If you have you basically want to inflate them make them as hard as you can, as they will tolerate and you will tolerate. Because if they're soft and mushy, you waste energy deforming them every time they land during the rolling process. Okay? All right. Yeah, I did that one. We're rolling backwards. Okay, so this is you do not want to skid your wheels to propel yourself forward and accelerate as fast as possible. You want to have the wheel roll. The other thing about skidding your wheels is that it damages the wheels, right? You leave behind the burning rubber means literally you smell the stuff and you can see it on the pavement, and you age your tires. So in the process of skidding things, it causes damage and it wastes energy, and that's the story of wasting energy. To show you where the wasting energy idea comes from, let's look at this. When I take a box like this and I push on it to the right and it moves the distance to the right, I do work on it, right? Correct. I'm using the word right in two different ways and it bothers me, sorry. So I'm putting energy into it. So I'll push it to the right and it'll move to the right, I'll do work on it. While the energy's in it, I was in it. For a brief period of time, the box was carrying energy with it in the form of kinetic energy. And then it slowed to a stop and had no kinetic energy. Where'd the energy go? And so this question then addresses that. So when the box skids to a stop on a motionless table, which objects do work on each other? I mean, we've talked up to this point about, well, when the escalator does work on you, you do negative work on the escalator, it's all very nice. Is that the case here? And so the question is, there are 5 choices. Who does work on who? Find your favorite choice, the one you think is correct, and we'll play vote. And you guys can actually, you could for a minute talk among yourselves and see what you can come up with the right answer here. You do work on something when you sort of force on it and it moves a distance in the direction of your force. So if you don't push on it or it doesn't move, you do no work on it. Work is the mechanism by which you transfer energy from you to it. All right. Come on back. How many think A, the table does negative work on the box, and that's all there is in the story? How many think B, the box does positive work on the table? How many think C, both objects do positive work on each other? How about D, both objects do negative work on each other? How about E, the box does positive work on the table, and the table does negative work on the box? E is getting the most votes, but let's look at that. The table, when this guy skids to a stop, the table is pushing the box to the left. You know that because it's slowing down. And the box is moving to the right. So the table is pushing the box in the direction opposite its motion. It's doing negative work on it. So that's for sure. So the table really is doing negative work on the box. You're all okay with that? For the box to do positive work on the table, which is the other half of E, what would the table have to do? Move a distance in the direction of the box's force. Where's the distance? Okay. Yes, you make the whole world move when you do this, right? But for all practical purposes, the table didn't move. I mean, okay, if you voted that it moved a teeny tiny bit, then okay, you're right. E is actually true. But for all practical purposes, the table did not move, and so the box did not do work on it. This is a problem. Why? It's because the table took energy out of the box by doing negative work on it, but the box did not give energy to the table. Where did the energy go? And the answer to that is the energy is still there. It got ground up into little teeny pieces by the colliding bristles. And it's still there, but it's in a useless form known as thermal energy. The surfaces got hot, or hotter, and the energy is now distributed as little tiny pieces sprinkled among all the atoms and molecules in those surfaces, and it's very hard to do interesting things with that anymore. In fact, you can't do work with it directly anymore. So the energy has been wasted. It's not been destroyed. You can't destroy energy, it's conserved. But you can grind it up and make mess out of it. So basically, it's like it went down the disposal. It's still there, but who wants it? Okay? All right, well, we'll move on with this on Monday.